So I'm going to be talking about some joint work with Wang, who is a postgrad student here with me at UNSW Canberra. And I'll be talking about pair correlation for real valued sequences. So the basic setup is we have a sequence of real numbers. Xn, indexed by the natural numbers. And we say that this has Poissonian pair correlation if the following holds. If we count the number of pairs in our sequence which aren't equal to each other, such that the fractional part of the distance is small. So the first n terms, and we're looking at the distance at scale s on n for some fixed positive number s. And if this equals 2s plus little of 1n, as n goes to infinity, then we say the sequence has Poissonian pair correlation. And the double lines denotes fractional part. So I guess in the context of number theory, the study of Poissonian pair correlation was initiated by Rudnick and Sarnak. And I guess they showed that for almost all alpha, the sequence of monomials of degree greater than 2 has Poissonian pair correlation. So I guess this problem has origins in the Berry-Tabor conjecture. From physics. And this is a statement about the distribution of energy levels of integrable systems.
Bryce, there's a question in the chat by Alex.
Yes.
So about the meaning of the almost all.
Almost all. This is with respect to Lebesgue measure. And the case D equals 2 of 1 is related to the energy levels of the so-called boxed oscillator. Now, since the work of Rudnick and Sarnak, research into Poissonian pair correlation, I guess you can split into 2 categories, which I'll sort of briefly describe as deterministic versus random, and for the deterministic sorts of questions, when does a given sequence have Poissonian pair correlation? And I guess one of the most heavily studied examples are when x and are consecutive values of some smooth function. And in these sorts of situations, the faster your function grows, the more difficult it is to establish Poissonian pair correlation. So one sort of theorem of this sort is due to Lotsko, Saw, Miletus, and Technow. And they showed that the sequence n to the theta has Poissonian pair correlation provided theta is a little bit smaller than a third. And then this result was sort of subsequently improved by Radziwill and Shubin. And they extended the range of theta to a little bit more than a third, 43 on 117, which is maybe an extra significant digit over the Lutsko, Sumerides, and Technow result. Now, getting theta much larger, I guess, is a really difficult open problem, and I'll mention the following folklore conjecture. If theta is not equal to a half, or it's not a natural number, then n to the theta has Poissonian pair correlation. Now, I will mention this is certainly not an exhaustive list of all the sort of interesting results, papers, and theorems in this area. I think this would just take me way too much time to describe the literature in detail. But I guess the point of this discussion is it's very difficult to establish Poissonian pair correlation for a given sequence. So the next question, which is often more tractable, given a sequence when does dilates of this sequence have Poissonian pair correlation for almost all alpha, and almost all in the sense I described previously. So, for example, the foundational result of Rudnick and Sarnak show that if xn is a monomial, then this is true. And in general, when it is true, I'll say the sequence is metric Poissonian. So one of the most one of the most important results determining when a sequence is metric Poissonian is due to Aistleitner, Larker, and Luca. And they made a connection between being metric Poissonian and the additive energy. So the theorem is stated as follows. Suppose we have a sequence of integers and suppose En, which I'll define right now. It's going to be the number of 4 tuples. Truncated up to n such that our sequence satisfies the following equation. So if this is a little bit smaller than n cubed, then our sequence is metric Poissonian. So I guess a few comments about this is this theorem is sharp in a sense. Trivially, we have En is less than n cubed because if we fix 3 variables, then the fourth is uniquely determined. And Bergin has shown if En is close to maximal, then the sequence is not metric Poissonian. So I guess there's still a few questions left open from this theorem. The first is what's the optimal dependence of delta on n? So if we let delta tend to 0 as n tends to infinity, how slowly can we make that happen? Um, and some results in this direction are due to Bloom, Chow, Gaffney, and Walker. And I guess the second question is there some characterization in terms of energy or some sort of combinatorial characterization, which is a if and only if statement? Now, a result of Aistleitner, Luckman, and Technow have shown that energy alone is insufficient to completely characterize the metric Poissonian property. Now, a third question, which is the focus of this talk, is does some variation of this theorem hold for real valued sequences? So if we drop the condition that they're integers. Now this is still open, and I guess the first sort of result similar to the real valued sequences was obtained by Aistleitner, El-Baz and Munsch. So we take a sequence of real numbers and we'll assume they have some spacing condition. I mean, some spacing condition is necessary, but this probably isn't the sharpest possible. So under these conditions, then if E star, which you can think of as an approximate energy, is small, then the sequence is metric Poissonian. All right, so E star is the number of 4 tuples instead of equality, they just have to be close to each other. Same equation, but close to each other instead of equality. So if this happens, if this is small enough, the exponent which came out of the Aistleitner, El-Baz and Munsch argument is 183 on 76, then we're metric Poissonian. So a few comments about this theorem. 183 on 76 is not expected. Well, now we know it's not sharp, but it's not expected to be sharp, and we expect that it can be replaced with the corresponding exponent for the case of integer sequences. So this is known to be true under the Lindelof hypothesis. Now, another sort of strengthening we expect is with the approximate energy. So E star it counts the number of solutions to an approximate inequality. And I guess the question is, well, how approximate do we need? And I think it's expected that we can replace this with we can replace 1 with 1 on n. And if true, this really would be the right condition, in the sense that it would be best possible. Anything better than 1 on n, maybe 1 on n plus delta, would mean that the condition which determines metric Poissonian property is less sensitive to perturbations than the actual property of being metric Poissonian. So anything better than 1 on n is not possible. So And it's sort of keeping the condition and the property oscillating sort of at the right range. So in joint work with Liang, we made progress on both of these problems. Now here's sort of a simplified statement of our main theorem. So we take a sequence of positive real numbers with the same spacing condition, um, and our approximate energy now at scale 1 on n instead of 1 is sort of at the sharp threshold. So suppose these two hold, and then this third condition 0.3, which I'll make some more comments about in a moment. So provided these three hold, then our sequence is metric Poissonian. So 0.1 probably isn't sharp. 0.2 is sharp. 0.3 probably is not sharp. So I don't think something like this can be dropped altogether, but it can probably be improved. Okay, so one way to think of 0.3 is that if our sequence of x's grows faster than a cubic polynomial. Right, and I guess you just put in your growth condition onto the left-hand side of this sequence, and that's enough to get the desired estimate. Um, Now, another thing to note is you can use an energy estimate to bound the left-hand side of 0.3. So why is this? I guess so. Partition your summation over n1 and n2 such that this difference lies in a small interval. And then apply Holder, or then apply like Cauchy-Schwarz, and then an energy estimate will pop out. So sort of using something like this, in general, we're able to also improve the condition in Aistleitner, El-Baz and Munsch's theorem to 5 on 2. Okay, so I guess why getting to 5 on 2 is significant is it lets us show that quantitatively convex sequences are metric Poissonian. And this resolves a problem raised by Aistleitner, El-Baz and Munsch. So establishing the relevant energy estimate relies on a theorem of Shkretov. And I guess another sort of new case of our metric Poissonian is polynomials of real coefficient with real coefficients. We're able to show these are metric Poissonian, and this resolves another one of the questions mentioned in by Aistleitner, El-Baz, and Munsch. All right, so this is sort of a summary of what we were able to show. Um, I'll go on to discuss some of the ideas which go into the proof. And our starting point is a theorem due to Rudnick and Technow. So suppose we have a sequence of real numbers which satisfy the following two conditions, 0.4 and 0.5. If these two hold, then the sequence is metric Poissonian. Okay, so 0.4, you can think of as just specifying some kind of spacing condition on our x's. Um, 0.5 is what we aim to reduce to an energy estimate. Now at this stage, I think it's sort of instructive to compare what happens in the case of integer valued sequences to sort of indicate why real valued is so much more difficult. Then in the case of integers, our conditions on summation in 0.5, we can replace being less than 1 by equals 0, just because everything's an integer. Okay, so now let's fix variables n and look at how this determines m's. So then our pair m1 and m2 lies on a line with slope given by a ratio of the x's. Now, the number of integer points on this line is going to be determined by the greatest common divisor of our expressions involving x. So once you count the number of integer points on this line in terms of GCDs, you can appeal to some theorems about GCD sums, or also sometimes known as Gall sums. Um, um, Okay, so I guess how this works is sort of GCD sums are going to reduce to an L2 norm of the number of representations of a given integer by a difference of the x's, and this L2 norm is turns out to be exactly the energy. Okay, so GCD sums are not available to us in the case of real sequences. So I guess one strategy is and this was sort of what was done by Aistleitner, El-Baz and Munsch. We can still sort of detect our equation by multiplicative characters. And doing this, you're going to end up with needing to estimate a mean value of Dirichlet polynomials. And the mean value looks like something like this. So our range of integration will be, I'll denote by capital T. One of our Dirichlet polynomials is formed by the x's, and the other Dirichlet polynomial is formed by the m's. And capital T is going to depend on the size of all our variables. So I guess if one sort of potential issue is if our x's are growing really quickly, then this is going to force us to choose a capital T to be quite large. And then the larger T is, the harder it is to estimate our Dirichlet polynomial on the m's. Um, so you can always reduce the size of T by using the fact that the above expression is increasing as a function of T. Oh, sorry, decreasing. And this lets you sort of control the range of integration to bring it back down to some sort of something of moderate size. All right. So now once we've controlled the size of T, the next step is to reduce summation over m to the Riemann zeta function. Um, okay, and this can be done by Mellin inversion. Um, so we'll end up with something like all right. So I guess comparing this with what we have above, there's no n there. So this n just came from rescaling our summation so we can bound by zeta on the half line. Now there's nothing really stopping you from choosing some other point in the critical strip, but I guess under something like Lindelof, we may as well do a half, because this is sort of what will give us square root cancellation as in sort of best possible. Okay, so um, now I guess if you assume Lindelof, uh, we can bound zeta over half plus IT by T to the epsilon. Put this bound into the above, and then sort of integrate the Dirichlet polynomial on the x's over T, and this will give you sort of the sharp energy condition. So what you'd be left with is just a mean square of an integral over the x's, and this is essentially works out to be an approximate energy. Um, And this is what gives the condition 3 minus delta. Okay, so if we don't have Lindelof, we can still say something, and this is essentially the argument of Aistleitner, El-Baz, and Munsch, and I guess sort of progress to Lindelof can be thought of in terms of like large values of zeta on the half line. So, or sort of moments, I guess, moments of zeta on the half line. So say, for example, you can do some interpolation between this moment and say a high moment of zeta and an L infinity bound for the x's and an L2 bound for the x's. And then sort of using the best available estimates for moments of zeta is sort of what will give you the exponent which occurs in Aistleitner, El-Baz, and Munsch. Okay, so and I guess I'll sort of mention there's some sort of parallels with this and an argument of Radziwill and Luco, who bound GCD sums by sort of detecting the relevant equation in terms of a random model for zeta, for which we know Lindelof is true. And I guess the question is, can this sort of random model be adapted to deal with the approximate energy case? And I'm not sure, maybe. Anyway. Okay, so the approach that Liang and I used to get our improvement is sort of different to this and based on some ideas of Heath Brown. In his work on gaps between smooth numbers. Right. So in this sort of in this work of Heath Brown, he's got a similar sort of moment of zeta and a Dirichlet polynomial with sort of very sparse support. And I guess the key idea in our setting is we sort of establish a number of estimates for our counting problem which modify lengths of summation. So if we've got sort of one inequality which increases lengths of summation, and another inequality which decreases lengths of summation, And if sort of these two inequalities are sort of disjoint enough from each other, we can combine the two into a recursive bound for our counting problem. And that's essentially what we do. The inequality which decreases lengths of summation is based on interpreting the problem in terms of lattice point counting over a family of lattices and doing some calculations with successive minima. And then the inequality which increases lengths of summation is based on viewing things as sort of a mean value of Dirichlet polynomials and then applying the Cauchy-Schwarz inequality in a suitable way. I'll stop the talk there. Thanks everyone for your attention.